So my name is Arnaud Furnemont. I'm leading the memory activities in iMac. We'll try to cover some different activities we do and maybe why is it so difficult to get a memory on the market. Still, I'm pretty excited to work on memory technology. I think it's the bottleneck for some time, and it will remain a bottleneck for, unfortunately, for some time again, because the data is only increasing, and it's extremely complex to put something new there. There is always a lot of excitement with new concepts, and there are many new concepts that try to get there. But the initial idea is, okay, it's good for standalone, it will be the key memory that will solve everything. And then after some time, you realize maybe it's not that good for standalone, we cannot scale, we cannot meet the specs. So maybe it's good for embedded memory, easier to meet, less tight pitch. Okay, still not working for embedded. Maybe for machine learning, now there are new things there, and we can try to put this new concept on machine learning. Unfortunately, sometimes not working either. Or then backup plan, security, PUF, physical unclonable functions. Maybe there it will work. If it really doesn't work there, you can even try to put a sensor out of it. And if it doesn't work, then you're back to the Mendeleev table and you start again. That unfortunately happens for some of the new memory concepts, and it's not great. But still, I'm optimistic, and I hope we can make something happening sometimes. Okay, so we're active in pretty much all steps of the R&D, trying to look on the paper on very weird or advanced concepts. In the lab, of course, and then we transfer to the fab at pitch. We also try to put it in a real circuit for in some cases. At volume, we cannot definitely don't do it in iMac. I guess to demonstrate something that is yielding at volume, we would need to use the entire fab for this particular project, and I guess my colleagues will not be very happy with that. What we also try to do now, and I still kept a dashed line because it's not extremely well advanced yet, is that we try to also to look at these new concepts at the system level. All right. So why is it that difficult? This is the classical one that you know. Usually we put latency here, and we put cost on this axis. And then the classical ones are all on this line, or sometimes a little bit curved, depending on how you put the axis. STTRAM, DRAM, flash, and backup storage, archival, hard drive, tapes. We were laughing about tapes yesterday at the debate, but it still exists indeed. Storage class now appeared. There is at least a first product on the market. Someone from a big memory company was telling me last week that most likely the biggest volume sold for storage class memory is used for reverse engineering now. But hopefully maybe this will become as well a real thing that makes sense in the system. So it's not just latency and cost. I put the retention, the energy, or the throughput, and the reliability there. It's very important. If you only meet the latency and the cost on this graph, it's not going to happen. You're above this, it doesn't mean that your memory cannot be used. It's just that it most likely be a niche market, radiation hard, something like that. If you hit the line or below, then you get biggest markets. Okay, specs. And what we do in iMac. There will be no unified memory. This is definitely something that will not happen. So I kept it by column of the full hierarchy, from the fastest and the more expensive to the slowest and cheapest. Try to put the concept that we are working on in iMac. I will mention the magnetic part, SOT and STTRAM for let's say SRAM area. Then for the main memory, we could try to put also magnetic memory there, or even a 3D DRAM. Storage class, resistive RAM is still a contender there, behind the PCM from the crosspoint. Also for low-end storage class, I would say we also work on Ferroelectric FET on this one. 3D NAND, I have nothing beyond that. Maybe here it's time to make a call. If you have any crazy concept that seems very crazy, but it's many bits, I'm very open to hear about it, and we can make it together. It's extremely difficult to beat the density of 3D NAND now. There is a very aggressive roadmap, but this aggressive roadmap will not last forever, maybe 3-4 nodes from now, and then after it's really nothing more that will make sense cost-wise. We also have some brainstorming on the backup of the backup. Also an interesting area, of course, less of a bottleneck for the system level. I put everything on the embedded side for, the node replacement, a little bit separated, but there again, the RM and the Amram are typically the main contenders. All right. One more thing, something that we don't really look at so often is the power. I put here as a unit of the power to write 1 gigabyte per second. It also follows the same trend, less and less power versus more and more. And if you cannot meet that trend, it's also over. And for instance, something I want to mention here is that the initial products with the cross point are not meeting that at all. They're actually higher energy than 3D NAND. And that's one of the reasons why it doesn't make sense yet, at least at this stage in the system. Also, plug and play of a new concept is also very challenging and maybe not the best idea. Typically, you will need to find first another application or something small to get to the volume, and then maybe it can really replace existing memory. I think Flash initially did not replace much, but progressively it killed everything like floppy disk, and then now it's killing SSD, or at least reducing, eating part of the hard drive market. So we really need to think about the full system and see where it could play a role. There are opportunities to optimize the system. This is it's absolutely still used every day, but there might be other ways to comprehend that. Okay, so before going to technology itself, this is also something that we are developing in iMac. Since we are doing a lot of pretty special new memory concept in iMac, it's a very good place to compare this. But again, as I was saying before, it's not just a matter of comparing the cell level specs. It also needs to fit somewhere. And so we are trying now to develop what we call the SEED, system benchmarking for enablement of advanced technologies. And that's where so basically it's a system simulator based on Gem 5. And then we try to see in terms of energy, power, performance to compare with existing memory and see where it makes sense to plug it. We are trying to include all this, but so far we are at the top level: SRAM, STTRAM, OXRAM. They start to be there in the simulator, and we go down as soon as we have data enough to create a compact model first, and then maybe design kit. Okay, so that's what we would like to do. A bit more in the technology side now. Embedded memory, clearly the STTRAM seems to be winning a part of the race in the sense that it seems that it has all the capabilities to play a pretty good role in the embedded space. Typically, it will be a one transistor to drive the current, and then one resistor. This resistor is made of many layers, but three main layers are the oxide that creates the resistance, magnesium oxide, and then a reference layer and a free layer. And then the magnetization of these layers, if they are parallel or if they are anti-parallel, we create a different resistance in the middle layer. So extremely good things about this memory is that it's extremely stable with cycling. You can go to very high cycle, normally 10 to the 12 or even 10 to the 15 is possible. It's also very, very stable with cycling as compared to any other non-volatile memory. This is definitely the most stable one. The noise that you see here is more linked to the fast measurements than the component itself. And the second extremely key thing here is that all the operating voltage are below 1 volt. This is an acceleration for breakdown, but every operation is below 1 volt, which is compatible with a conventional logic. Which makes it, again, very, very interesting. It looks like the big ones like Samsung, TSMC, and also Global Foundry plan to have it on the market very soon. And again, mostly because of this advantage low voltage, and good reliability, including non-volatility. Something else that we are working on is the spin orbit torque, which is really much less mature than spin transfer torque Amram. It's the same concept. You have also a free layer and a reference layer, but on top of it you have, on bottom of it, you have a spin orbit torque layer to be able to switch this free layer basically. You put a current not through this but through the bottom layer, and this will be able to switch flip the magnetization here by injecting a spin current in this free layer. And again, similarly for the read, if the reference layer is parallel to the free layer, the resistance across this tunnel barrier will be lower, and if it's anti-parallel, it will be higher resistance. It's still more complex because now we have 3-terminal device plus most likely a couple of transistors. But what is interesting about this concept is that now it's extremely fast. STTRAM can go down to 20, 10, and 5, maybe 5 nanoseconds, which is great for low power but low performance SRAM, or to replace embedded flash, for instance. It's not good enough to have the full SRAM replacement in more advanced systems. So this one, the torque that is exerted on the free layer magnetization is perpendicular to it, which means that you can really you have no precision time to flip the layer, and this can go below 1 nanosecond flipping time, and then you can compete with SRAM. The physics behind are quite heavy, and we even that, for instance, what part is due to the spin Hall effect, what part is due to a rush bar interaction is not clear. But I think I have it on the next slide. As I was saying, the main advantage is the fact that the writing speed can be sub-nanoseconds. There are challenges, and that's what we are trying to tackle in iMac. The efficiency of the flipping, so the writing current density. This metal is usually it's a heavy metal, let's say a tungsten, for instance, and we need absolutely to reduce this current density required to flip the devices. But the biggest one, and this will make it or break it, is the zero field switching capability. Right now, to be deterministic, you need an in-plane magnetic field in the device, which is extremely unpractical for real applications. It's a very small field, a few millitesla, but this is still too much. So actually, the main goal of our research right now is to see if we can remove this need of the additional field. But I think we have integrated now for the first time on the 300 millimeters this spin orbit torque Amram. So hopefully, if we can fix this, then it becomes a contender for SRAM further scaling. A lot of things have been said about resistive RAM. So again, for embedded space, it's still well alive, and the OXRAM is the most simple one of them. So it's very easy materials. It's like hafnium oxide or dioxide. We have mentioned that multiple times during the week. The problem is that it's a filamentary element, so the memory is done by pushing some defects, some oxygen vacancies to this oxide. When the filament is complete, well, the resistance is low, and when you open it with a reverse field, a reverse voltage or a reverse current, then the resistance is higher. And the problem is that if you switch it with very low energy, lower current, then it starts to be a very much thinner filament, and the bottleneck is really defined by 2, 3, 4, 5 defects, and it's extremely unstable because of that. If you start to put more energy during the write, more current, then the filament will be bigger, thicker, and then it becomes much more stable and much more readable. But as you can see here, this is a pretty aggressive retention test. It's a reflow test to emulate the packaging. So up to 260 C for a couple of minutes is one of the biggest retention tests that an embedded memory has to sustain on volatile. You can see that you need to go even up to 200 microamp to be able to have decent, to avoid big tail creation. So it could be nice in some applications, in not so advanced logic nodes, and this is of course much easier to make than Amram, at least the first time, because it's much easier materials. but it does not have all the qualities of the MRAM in terms of voltage and current. All right, standalone memory now. This is the big one. I guess that's maybe the main bottleneck in the systems is the DRAM. DRAM roadmap exists, it continues, but it's still slow. It's not at all 1.4x per year or something like that. It's slower than that. And we can see that there are many transitions that are going to happen in the roadmap to even continue it. Right now, you know, it's a transistor that is not a flat transistor. It's something like a U-shaped transistor, and then there is a big capacitor, very, very high aspect ratio because it's very squeezed. And this capacitor has a double-faced layer here to double the capacitance, as simple as that. So it's like a glass, the shape of a glass. So multiple transitions in this roadmap that we think. Again, this is what iMac thinks. We don't have access to the internal roadmap of the companies. It's based on what we know about the technology and what we see is possible. Half of the die in DRAM is the periphery, so moving to more advanced logic will happen. Right now it's still silicon oxynitride logic. Moving to high-K or to even FinFET, we see it as a first transition happening relatively soon, actually. Second transition would be to move to pillar. So there is no more room at all to put a full glass shape and a double layers. So you have to go to a single pillar and then you cover it with your high-K layer for the capacitance. And then you could go toward the ferroelectric concepts to enable less or lower aspect ratio DRAM. I think I will talk 2 minutes about ferroelectric after. If you come back to the transistor, if you want to reduce even the footprint of the transistor, you need to go to 4F square transistor. But I think it would make sense only if you also go to the back end, so that you can even put it on top of the periphery. So now we are back to TFT, and actually we are looking into some of the concepts that were explained earlier this morning on the on big electronics, because they use TFT, very big size. So here, of course, it will have to be scaled extremely aggressively, but there is some material that are interesting that could be also tried for DRAM application. Even for that, it could go down from 18 nanometers, that is the most recent Samsung product, maybe to D12, but to go really to D10 and below, you really need different concepts, really a 3D DRAM or stacked MRAM, something that is more disruptive than what it is now. The ferroelectric DRAM, that was an interesting concept here. There are some basically the ferroelectric came back fashionable for a few years now because of the orthorhombic phase of the hafnium oxide. If you dope the hafnium oxide with certain amount of certain materials, you get orthorhombic crystalline phase, and this one is ferroelectric down to very thin layers, like 10, 8, 7 nanometers is still ferroelectric. And if you sandwich this layer between two metals, then the cycling is actually very good. You can have a lot of cycles on this layer. That's why 1T, 1C could work, one transistor, one capacitor, ferroelectric, could work as well for some DRAM applications. Some also are proposing MIS structures, but the problem there is that when you put it in contact with the silicon, you introduce some defects and carrier trapping, and then the cycling is dying quite soon. We're also looking at the ferroelectric, but for a lower, slower application, denser. So we put ferroelectric FET, but in a 3D mode to like a 3D NAND, but to enable a storage class memory a little bit denser than the initial course point. Scaled MRAM, yes, it's a possibility, but it will require, we are making some progress in the patterning and very dense MRAM. But the key point here is the selector. What are you going to put as the device that will select this MRAM? Is it going to be a TFT 3D, or is it going to be a two-terminal selector? That's something we are also looking at. Storage class memory, I was also mentioning that we are looking at the 3D ferroelectric FET there for storage class memory applications. Right now, you know what is there, the PCM and OTS, overnic threshold switching, which is the cross point from Intel Micron. And then Samsung also is proposing a Z NAND, which is effectively a 3D NAND, but a single bit 3D NAND for similar applications, because at system level, this is all pretty much as fast as this. Again, storage class is also a very, the key challenge is similar to the DRAM, one of the challenges of the DRAM is the selector. To avoid a sneaky path, you need a very, very good selector that's an off state at half the bias. It has only to be able to, it has to be at the nanoamp level, and when it's on, it has to be at tens of microamps level, and that makes a pretty big thing for the, maybe the cross-point main innovation was actually the selector that enables this. Storage class memory scaling. There are many ways to scale this storage class. So if I start from the cross point as the initial product, you can have lateral scaling. You can have also more than 2 layers. Right now they have 2 layers. And but what we are also looking at in iMac is the vertical integration. So keeping the thinking of 3D NAND, but now for resistive or PCM memory. Looks like I will be pressed by the time here. I see my boss here that is complaining already. One thing about 3D NAND, because that's the one that is very interesting. Right now it's 64 layers in production. It looks like there is a path to 200 layers or maybe even 500 layers by stacking in multiple passes. So you put an edge stop layer in the middle and you do it twice. But nice, you can maybe do it 4 times, but beyond that, the cost-wise, even if engineering-wise it can be done, cost-wise it will not be possible to improve the cost further than that. So 500 layers seems amazing, but actually it's not that many nodes ahead from now. 64, if we double each time, it's only like 3 nodes from now. 3 big nodes, right? You can have intermediate 96 layers and so on, but so what is beyond that, it's totally unknown. Okay, 2 last slides on the long-term futures and conclusions. So I think every research in memory can be summarized in these 3 questions. Very low power embedded memory for all portable applications. I was mentioning STTRAM and OXRAM that can enable that. What's next? We don't know, but there are concepts on voltage controlled and SOT maybe that can also enable this part. Maybe that's the one I'm less worried. I think there are many concepts that can go to very low power for embedded. The storage part, a little bit more worrying. We cannot even store everything today for the budget that we have. This will not fix everything. Tape roadmap, hard drive, 3D NAND roadmap will not solve everything. So we need to look at very, very fancy things, and this is nowhere close to being maturity. And then the biggest issue is the DRAM bottleneck. All this is nice, but is not going to fix completely the DRAM bottleneck. So most likely there we will need to go toward different even architectures to have that. So again, that's something that we take into account, and we would like to go from the system point of view, what would needs to be. But that's again a very different people, very different skills that we need to interact with. We need to be able to talk the same language. So we are really trying to do now the system technological optimization to enable the future. And also there, any collaboration will be great, because we're also missing this connection between new concepts and the full system. And that's it. Thank you.